Today, with great honor and pleasure, we have Pensai, along with Commonwealth Publishing and Tang Prize Foundation. We invite Dr. Honjo to Taipei to give us a speech. Dr. Honjo is a laureate of Tang Prize, professor of Kyoto University, and the top class scientist in Japan and the world. PD-L1 he discovered shed light on immunotherapy of cancer. We can't wait to have Dr. Honjo to talk about his research, his pursuit of science, and his words to young scientists in Taiwan. But before that, let's welcome the chief editor of Commonwealth Publishing, Mr. Wu Yunyi 小姐, to give us a few words. Please, a round of applause.
大家好，很高兴我是天下杂志出版的总编辑吴韵仪，很高兴在下午的时间可以跟大家见面。执行长好，然后 Dr. Honjo 好。我想呢，天下杂志，很高兴在今年年初的时候，我们跟唐奖一起合作出版了《永不放弃》这本书。那这本书其实是讲5个世界顶尖的科学家，他们在不同的领域，包括人文社会科学的研究，然后他们在顶尖研究里面，他们长期耕耘，最后能够影响世界的故事啊。那很高兴我们有2次的合作机会，今天我们是跟唐奖邀请到这个我们第2位的讲者，在今年年初的时候，我们还邀请到了是法治奖的得主来到台湾。那然后呢，我们也很谢谢今天的共同的主办单位 Pensai。那这也是天下杂志很难得有机会可以跟一群科学界的朋友，然后跟一些很年轻的科学的新生代，大家一起来对话。那我们觉得其实科学的进步其实是非常的快速，而且在很多的领域里面都有很大的突破。我还记得在今年年初的时候，天下杂志邀请到在美国很重要的一位创投企业家Peter Thiel， 他来到台湾。那个时候他要讲，其实他在自己的这个文章里面他就有写到过，他说其实科学界的这个发展是突飞猛进，可是我们现在居然只把它用在140个字的变化，他讲的是 Twitter。我们看到的很多的新的变化，他说其实都是科技里面的一些小花招，可是呢还有更多的世界等着我们去发现。那很高兴今天我们可以邀请，就是说能够让 Dr. Honjo 来跟大家见面。那我想说，其实今天应该要先帮我们这个主要的这个演讲人来了解一下，大家现场到底是有哪些的听众。Please raise your hand if you are students. Wow, 70%. 如果你是跟 medical related, raise your hand. Medical related. Okay.And bioscience related? Okay. You are just a fan of Dr. Honjo. Please raise your hand. Thank you very much. 好，那其实真的非常的难得。那我觉得像这样子的学习跟这样子的讨论，在台湾这个社会尤其需要。我们过去有非常好的基础，我们常常可以看到，就是我们在科学领域的学生在世界上面。有很好的表现可是呢，后来他们就慢慢的消失，因为我们的舆论它其实没有非常多的重视。那我希望未来有更多这样子的活动，可以出现在我们的社会里面。我记得我读过一句话，可是我已经忘了这句话从哪里来的。他的意思是说，我们常常看到一个新的发现的时候，我们常常是 overrated the impact in the short term, but underrated the impact in the long term。我们常常忽视了一个改变它的长期的影响。那我相信 Dr. Honjo 他的研究的发现对我们是有一个长期的影响，而且对人类是有非常大的贡献的。那谢谢大家。
谢谢总编辑 ，Thank you, Ms. Wu. Now let's welcome the CEO of Tang Prize Foundation, Mr. Chen 陈振川陈执行长。
Good afternoon, ladies and gentlemen. Welcome to National Taiwan University. I was the Dean of General Affairs around 15 years ago. Yeah. If you can find that the campus becoming splendorous. That's my contribution. Yeah, everybody knows. Yeah, 陈振川，我是以前的总务长，我把整个台大校园完全改变，变成国际最漂亮的大学，特别是舟山路、椰林大道，还有整个包括附近的这个环境，所以跟你们介绍一下。It was roughly this time, the foundation announced that Professor Honjo is one of the recipients of the Tang Prize in Biopharmaceutical Science. 1 year later, we are very happy that Professor Honjo come again to join us. In past few days, he visited Taiwan for a cultural trip. And this morning, he attended the 5th Society of Bioscientists of American International Symposiums in Academia Silicon. He gave an enlightened speech over there. And just now, he joined us in this room to present his achievement. It was greatly appreciated in this morning's technical speech. But this seminar co-sponsored by Penn Science and Commonwealth Magazine. I had to thank them for co-host such a wonderful events. And I hope in some days, the young scientists here, one of you, will stand on the stage of Tang Prize awarding ceremony and receive the honor, just like what Professor Honjo received last year. And I wish you all have a nice afternoon. Thank you very much. Thank you.
Next, let us welcome Dr. Honjo to give us a speech. Please, a round of applause.
So good afternoon, ladies and gentlemen. I'd like to introduce some of the basic knowledge which you already know. This is a picture of the number of cancer deaths all over the world per 100,000. So you can see variety of the color all over the world, and the area where we live is kind of the average. And that is about 100 to 150 people per 100,000 die every year. And the area where the color is pink, they die before they get cancer. So there is not significantly they are protected from the cancer, but they die before they get cancer. So that's a difference. But in any way, we have about 14 million cancer patients in 2012, and this will enormously increase every year. And at this moment, every year, about 4 to 5 million people die all over the world from cancer. So when the doctor diagnoses cancer, you go either operation or irradiation, or you get a pill to treat the cancer. However, this is the statistics in the United States. This is the number of the deaths by lung cancer, and this is the prostate cancer and pancreatic cancer. And the number of the deaths is still not really improved, even those treatments. There is some decline of the deaths by lung cancer. But I heard this is not because of the good treatment, but more contribution from the diet. The United States people recommend the low-fat diet that helps the cancer incidence a lot. That helps the reduction of the death. So I'd like to introduce the fourth treatment of the cancer today, which is called immunotherapy. The idea of immunotherapy has been around over 50 years. This was originally proposed by Burnett, who got the original founder of the immunology, clonal selection, the basis of the immune diversity. He developed the modern immunology. The idea to stimulate our immune activity and attack our cancer cells has been around, and many people try this. The most common idea is to identify antigens expressed on the tumor cell. So immune cells recognize tumor cells different from our body, so they begin to attack. That's the idea. So therefore, the scientists try to identify cancer-specific antigen, just like virus or bacteria. And once they find those antigens, they generate those proteins or peptides and inject. This has been tried many years, many decades, and so far no success. People also tried to take patient's lymphocyte out of the body and stimulate in vitro and put it back. This way, immune system become rejuvenated and attack the tumor cell. That's the idea. Again, many trials and no success. Third, there is a hormone-like proteins in our body, which makes the immune cell active or inactive. And those which activate immune cell was made in a recombinant system, E. coli or yeast, and injected it in human body, like interferon, gamma, alpha. But again, there was no success. So all these trials is try to push our immune systems, stimulate. So when I compare this, the driving car, it's like a pushing axle and no success. Today, what I like to introduce you is the blockade of negative immune regulation. This is like brake is too much, then our immune system is not working appropriately. So instead of pushing axle, you just release brake. That's the idea, what I'm trying to introduce you today. And those brakes, we have two major ones in the immune system. The first one is at the stage of real initiation. And we call this like getting out of the parking lot. So when you drive a car, you have to initiate your motor. That is the antigen recognition by antigen recognition receptor on immune cell. And then they are equipped with two regulatory components, CD28, that is equivalent to axle, and CTL4, that is equivalent to the brake. So if you have too much brake, car cannot get out of the parking lot and stay in the parking lot forever. So blocking the brake release the car out of the parking lot. But that is not enough. You need effector phase that is equivalent to running on the road. And here again, you have the axle and brake. Once you get out of the parking lot, the activation is through just seeing the antigen by antigen recognition receptor. And then the brake is to control the speed of the automobile on the road. This regulation by PD-1, which I studied, actually I accidentally found this molecule almost 22 years ago. The reason why we encounter this molecule is purely fortuitous. One of my graduate students working on the project to identify thymic protein in thymus is a place when the lymphocytes are selected. In the immune system, the key point is not just simply attack the invaders, but also prevent attacking ourselves. Okay? The immune system needs these two properties, attacking the invaders, but not, so this is just like army. If your army attack the enemy, it's perfectly okay. But if the army shoot against your people, it's a disaster. Okay, this is the most important regulatory system for immune mechanism. So the idea is how to select those lymphocytes which can attack cells. And then we have to remove those cells. And in thymus, here you have the specific organ where all the T lymphocytes have to go through after generation and have to deliver to the periphery in the blood, in the whole body. They have to go through the examination. And this is the mechanism for the apoptotic selection in thymus. And my student wanted to identify this protein, and he carried out the subtractive hybridization. And simply, you stimulate thymocytes, and you don't stimulate, and you see the difference. And those which are stimulated, appearing molecule, he collected. One of them is the protein called PD-1. And this is highly expressed in stimulated thymocyte, but not non-stimulated. And the structure comparison suggests this must be very important molecule because they have highly conserved amino acid, which is responsible for sending the message into the cell. So we thought this protein is interesting to worth investigation, but we don't know what this molecule is doing. So the simplest and straightforward the strategy to find out the function of the molecule, which we don't know, is to destroy the gene of the molecule in the animal and observe what happened. And we have done this, and the student, Dr. Nishimura, carried out this program and created animal which doesn't have PD-1 gene. And he hoped something happens. After 6 years of work, he found nothing happened. He was very much disappointed. but he has to publish some paper to get his thesis. So we wrote something, but it's not that exciting. And then he just kept the mice for nothing, just waited. After 6 months, he found very interesting observation. Mice began to die after 6 months. And then he analyzed the dead mice, and he found something wrong. And this is the black mice, 57 black. So mice are normally genetically pure, unlike human beings. So each individual sitting here have different genes. But when we study mice, we make the gene of mice homogeneous. So that way we can test and compare many mice under the same condition. So the black mice showed kidney problem and joint problem. And white mice are the heart problem, as you can see here. This is very similar to what we have in human, dilated cardiomyopathy. And I believe this is the autoimmune diseases, but none of the cardiologists believe, and they don't treat patients as autoimmune diseases still. But that's the side story. And basically, all the animals which lost the PD-1 gene has activated immune response, that way attacking your own body, not just simply attacking the invaders, but their own body, depending on the genetic background, different target was severely damaged. Sometimes kidneys, sometimes joints, sometimes heart, sometimes pancreas, insulitis, sometimes myocarditis. So when we found this, actually Nishimura finally published this finding 1997. So finally he was awarded. But at the first time, when he tried to get the results soon, he was very much disappointed. We thought if we can enhance our immune system, we may be able to enhance our activity against tumor cells. So I suggested the other student try to this. And this is kind of very straightforward experiment. You inject the tumor into mice and see what happens. If you compare PD-1 deficient animal and normal mice, and what happens. So this is the white mouse receiving the myeloma cell. And the myeloma cell grew very quickly. This is the day after inoculation. However, when this was injected in the PD-1 deficient animal, no tumor grew. So this is very clear observation. And then we went on to inject antibody. This is against ligand to block the PD-1 signal. Then similar phenotype. The tumor growth is very much disturbed compared to the control IgG1. And the survival of animal also prolonged. So, obvious, we are very much convinced. This is so clear. So why not? We should go on to human clinical application. We also tried whether metastasis also blocked And this, again, a very simple experiment to inject the melanoma, black tumor cells, and see the liver from the hematogenous metastasis. This is a PD-1 deficient animal, and this is the melanoma growing liver. So it's so obvious. And antibody treatment also show reduction in the weight of the liver. The application requires production of the humanized antibody. We cannot inject mouse antibody into patient. So I tried to persuade Honjo pharmaceutical company to create humanized antibody, but of course Honjo never tried that. I mean, they don't have any expertise or the technology or knowledge to make that. And it took almost 1 year until I could persuade. Many different companies contacted by through Honjo refused. And finally, very fortunately, Medalex, which is a venture company in the United States, and other expertise to create humanized monoclonal antibody, approached to Honjo and proposed a collaboration. And they started and made humanized anti-PD-1 antibody, which was approved as a new investigation new drug by FDA that allows the clinical trial. And the clinical trial started 2006 and 2009 in Japan. So the clinical trial is to ask the volunteer patient to receive this unknown treatment. So at that time, as I said at the beginning, the older patients who were diagnosed as the cancer receive the surgical treatment, irradiation, and the chemo. And normally, no doctors recommend patients to go on the immunotherapy. So all those patients who are kind of hopeless volunteer to this type of the clinical trial. And unfortunately, they got very good response. 20 out of 31 respondents showed very long-lasting cure. And this is the size of the tumor. So this is a 0. And patients who didn't respond increased the tumor volume. But those responded reduced the size of the tumor. And it lasts very long. This is by week. So under 30 weeks is more than 2 years. So this was a very kind of the shocking to the clinician. And then many volunteer patients was easily attracted to the clinical trial. So this is our own clinical trial in Kyoto University Hospital, and we aimed ovarian cancer in collaboration with gynecology department. And we advertised only those who were treated by platinum treatment, and they were shown to be not responding. And this is one typical case, and actually we have only 3 cases who responded very well. This is the one, probably the best. When the doctors show this kind of picture, those are usually the best ever. And you can see very quick reduction in the size of tumors. And this lady recently interviewed by NHK and said she was almost dying. And doctor said 3 months the best she can survive. And now she is playing golf. So that was very impressive. In the same way, the patient who responded, very long, durable response. This is quite distinct from the other treatment. And so recently, and more different type of cancers are shown to be responding to the PD-1 treatment. This is the Hodgkin lymphoma, hemogeneous blood. This is the B-cell lymphoma. And this is the randomized study of non-treated, the patient, melanoma patient, who have not been treated by other cancer treatment, chemo or anything, were now chosen, so randomly divided in two groups. Those who receive alkylating agent, dacarbazine, and those who receive anti-PD-1. And you can clearly see big difference in survival curve. Patient who received the PD-1 survived something, the 70% after a year and a half, and those who received dacarbazine going down very drastically. So therefore, this randomized study was stopped. Another phase 3 trial for the advanced squamous cell lung cancer. And here again, the best chemo treatment compared with the PD-1, and again, you can see clear difference. So looking back, since we first identified the PD-1 1992, we went through the very difficult period to identify the function of PD-1, and very fortunately, we showed the effectiveness to the cancer treatment 2002, and then humanized antibiotic was generated by the owner and the Bristol Myers. The Medarex was later bought by Bristol Myers Squibb. And the clinical trial initiated, and then 2014 it approved by Japanese and US authorities as the treatment of melanoma. And this year it was also approved for lung cancer. So the point I'd like to tell you from this table is, first, it takes a long time, more than 20 years from the first observation to the actual application. So this is the typical of the biomedical science. It's totally different from the engineering of Professor Chan. You can design the project and make the construction. But in case of the life science, you never know which seeds will grow and make a fruit in the end. So you have to spread many seeds and put the water and many seeds. And you have to wait a long time. That's why I'm always asking the government, life science is different. You have to have long and very patient perspective to support. So I'd like to summarize what is the advantage of anti-PD-1 therapy. It's less adverse effect compared to all other types of the cancer treatment. And secondly, it's effective wide range of tumors. And also, it continues to be effective. And also, it can be combined with others to enhance the effectiveness. So why this is the case? I think this is because our immune system has enormous diversity. Our immune system can recognize the virus which we have never encountered, like HIV or SARS or the MERS. People never seen these viruses, but still we can attack. This is because we have huge, uncountable number of diversity in our body. So, for example, cancer cells normally treated by drug, but they mutate, they change. So drugs may not be effective after 3 months or 1 year. And again, you use new drug, and again, they mutate, and all these tumors surviving different type of cancer drug are resistant. But immune system can recognize all these mutant cancer cells as a not self, so they begin to attack. We have enormous repertoire. This is the advantage of the immune regulation. And in fact, this is the case. This is the colon cancer, and they divide in two groups. Those who accumulate mutation, namely they have lost repair mechanism, and those which do not mutate. So clearly, the tumor cell which frequently mutate can be more easily recognized by immune cell and very effective target of anti-PD-1 treatment as compared to less mutating tumor cells. And also, as I said at the beginning, we have two breaks, the CTL4 and the PD-1. This is a combinatorial study. The anti-PD-1 and anti-CTL4 makes the effect over 50%. This is the case of melanoma, and tumor reduction rate. And the effectiveness is very nice. So this is the recent study published May 31st. And this is a combination of PD-1 and CTL4. And this is the size of tumor. The 0 means the same size, and this is the increase of tumor size. And this is the reduction of tumor size. You can clearly see PD-1 alone and CTL4 alone combined is far better. So this way we'll be able to increase efficacy of immunotherapy. So in future, I believe immunotherapy by checkpoint blockade will be the first choice of the cancer treatment. And we can combine, for example, low doses of irradiation or chemotherapy to destroy part of the tumors and expose the antigens, and that will activate, combined with anti-PD-1 or CTLA4, will be the ideal for treatment of the cancer. So the next challenge of our immunotherapy is, first, we have to remember, although the side effect is far less compared to other treatments, still we have lots of the possibility of autoimmune symptoms. And this we never know. Depending on individual, different organs are attacked by autoimmune diseases, depending on your own immune capacity. And secondly, depending on where and when you start the tumor treatment, non-responder exists. So we have to find out the best way to treat all the patients. And also, it's ideal to identify markers to tell responder and non-responder before we start the treatment. So for the young people, what I try to convey is the life science is very unique aspect of the natural science. the medical science advanced a lot, but there are still lots of the black box, and many experiments are try and error, and you have to continue, and with lots of passion and curiosity, and that's the only way to reach goal. And unfortunately, we cannot predict what will happen. And on the other hand, that is the beauty of life science. You may be lucky enough, and then the molecule which we accidentally identified, PD-1, is now the best target for cancer treatment. So you may find such a lucky occasion in your future. Thank you for your attention.
In the following session, we will invite Dr. Honjo and the two young scientists from Taiwan to have a short discussion about their idea about Dr. Honjo's research and their questions. Please, let's welcome Donna and Kevin and Dr. Honjo again, please. Yes. Okay, I I think you don't know Kevin and Donna before this event. Kevin and Donna are students from National Taiwan University, and they are graduate students now, and we recruit them to join this talk with Dr. Honjo. And before we start the conversation, maybe Kevin and Donna can introduce yourselves, and maybe I can ask you a few questions. Okay, maybe Donna, would you like to introduce yourself?
Hello everyone. Thanks the Dr. Honjo's exciting speech. I can get a lot of knowledge from his speaking. My name is Donna, a graduate student from the National Taiwan University Institute of Physiology, and I came from the gastrointestinal immunity lab, and I study on the mechanism of the irritable bowel syndrome, which may link to the immunity and the tolerance. In this semester, I study on the gastrointestinal mucosal immunophysiology, and then learn lots of the issue of the immunity. So I'm glad to have the chance to participate in this speaking. Thank you.
Great. A round of applause, please. And Kevin, please introduce yourself.
Good afternoon, everyone. I'm Kevin. I'm a student from the Department of Parasitology, National Taiwan University, and recently I'm working on a parasite called Trichomonas vaginalis. So in the parasite infection, we all know that the immunity plays a very important role to defend us from severe syndrome. However, in the case of cancer, the cancer cell could hijack the immune system and utilize it. So I was already very excited to participate in this talk, and I really learned a lot today. Thank you.
Okay, great. Okay, before you two ask questions to Dr. Honjo, I would like to ask you both a question. Kevin and Donna, do you want to be a professional scientist in the future? Or if yes, why? If no, why? Donna?
I think maybe. I feel in this. I'm a junior in the graduate student. In this graduate, I think in the study in the research, I feel exciting about to investigate or further investigate the interesting thing I want to talk or the mechanism in this issue. So maybe I think it maybe.
So your answer is still maybe. Haven't decided yet. What stops you from making the decision? Your professor?
No.
Your boyfriend?
No. No.
No?
Maybe I think it's the money.
The money? Do not let money stop you from everything. Okay? Okay, then how about Kevin? What's your decision?
Yeah, I would like to be a scientist if possible, because be the one to discover the mother nature. I have to say it's really cool, and that's why I would like to be a scientist.
Okay, cool. So nothing is stopping you.
Of course, the foundation is also.
We have Tom Price Foundation over here. Right? Okay, then your questions to Dr. Honjo. Maybe Kevin first.
I get a question from the talk. So we know that PD-1 could be a target in the cancer therapy. How about other diseases such as the autoimmune disease or infectious disease? Could we utilize PD-1 as a target? Thank you.
So PD-1 is the brake of the immune system. So if you push a brake, the immune system goes down. So that helps to treat autoimmune diseases, because autoimmune diseases are the disease caused by hyperimmune reaction. So to treat, you need suppress immune system, and that way you need not blocking the PD-1, but pushing the PD-1. And anti-PD-1 is the medicine to block PD-1. So this will be opposite for the autoimmune disease treatment. But in case of the infectious diseases, you need activated immune system. Therefore, PD-1 antibody is very suitable for the treatment of difficult infectious diseases like HIV or hepatitis B infection.
I have another question about the attitude in the research. Persistence is plays an important role in the research. If you give up, everything is gone. Is there a path to support the Dr. Honjo? Can you give us some support to our teenager, just like me?
So I think when I was young, we are very poor, so we don't worry about the money. Okay? When you are poor, anyway you are poor. Okay, no matter what you do, so that's not a big problem. But when they, Taiwan and Japan and the economy developed, you can have a chance to become rich. But if we don't have the chance to be rich anyway, we don't care about the money. But now, the many developed countries have this problem. So the young kids are not that hungry anymore because they have so many different opportunities. So to be scientist, I think the most important thing is curiosity. Okay, if you have some mind, wow, this is very strange, why this happens, then that's the starting point. So the most important thing is don't trust textbook. Okay? If you believe everything written in textbook, that's the end. Everything is solved. But most of the textbook, if you read carefully, there are so many things which is very strange. Why this is the case? But authors have to write something, so they make up the story. That's a textbook. So the number one criteria to be scientist, don't believe in textbook. Okay, this is, you can read, but don't believe everything. You have to have some doubt. And so for that purpose, you have to think your own brain and find out why this is the case. And then you stimulate your own curiosity. You want to know why. This may be wrong. And I think this is the beginning of everything. And then you certainly need some courage to challenge this big question. Normally, a big question is very difficult to solve. It takes years. So nowadays, the big problem is scientists are so competitive. They want to publish the paper so quickly. So they choose easy problems. And they choose the problems which are popular. So everybody wants to solve this problem. And they join the game. So there, the competition is so tough. But those questions are very popular. And once you solve or even close to solution, the paper can be accepted in many famous journals, like Science or Nature, which you like, right? But I'll tell you, none of my paper about the PD-1 published Science, Nature, or Cell. And usually, the question which is not the popular is usually very deep. So people don't care because for them, they take it's kind of the granted. But if you think deeply, this is very strange. That's the beginning of the big question. And those questions are very difficult. And usually it takes time. So it's a big challenge, and you need courage to tackle.
Dr. Honjo, I'm curious about how do you tell Dr. Ishiwata, your student, after 6 years of no result, how do you comfort him? Or you just say nothing?
So that's a very difficult time. You know, the students are unhappy, but professors are also unhappy, of course. After spending 6 years, and so only thing I could say is, well, let's publish something for your thesis, and then fortunate. So I didn't have any idea, but simply just he didn't kill all mice at that point. He kept the mice, and fortunately, after 6 months, they begin to show some symptoms. But if it took more than years, it could be no finding. So purely this is luck. So for this part, I have no advice. You need some luck.
So persistence is really important. And if you persist enough, luck may come or may not come. Okay. Kevin, Donna, do you have any other questions?
I have a follow-up question.
Okay.
So is there any obstacle on the road of your research that you could share with us today? Obstacle, challenge, obstacle.
What's the major challenges and obstacles you in your case?
So this PD-1 story, scientific part, I explained. So the initial difficulty to reach the conclusion this is the negative regulator took 6 to 7 years. But once we solve this problem, scientifically it's very straightforward to apply to tumor experiments. So that part very straightforward. And then the next step to really apply to the clinic. This is a totally different level. Okay, you cannot do experiment on a human patient. Okay, so it takes very careful preparation, and you need large scale operation. Well, you need money, okay? To prepare the humanized antibody. It's not easy job. So you have to convince people. So at that time, I had a lot of problem because the Kyoto University at that time has no capacity to apply patent. So I have to invite Ono company to have them to write the patent application and pay the fee for the patent. Okay? So Ono didn't know anything about the PD-1, but they simply agreed to apply patent and kind of the co-owner of the patent. So then I have to persuade the company to carry out this very expensive clinical trial experiment in synthesizing the humanized antibody. It's a big investment. Of course, I don't have money. So the company who challenged this new project was not that easy. So as I explained, it took more than a year to come to the help of the Medalex and Ono joint venture. So well, once they started, it went relatively smooth. So that's the initiation was very difficult.
To persuade the company and to wait for the venture capital to join, that's a difficult part for a scientist to fulfill that. Okay, Donna, do you have any other questions?
I have some. In your speaking, I saw you said about the 70% immunotherapy in the non-responder. I think it's very not courage to us to everybody. Can Dr. Honjo say what's the major cancer in your PD-1 immunotherapy?
Okay, still 70% of people who will not respond to the PD-1 therapy. And of course, Dr. Honjo said that we still need a lot of research in knowing why. But Dr. Honjo, do you have any idea in this question that people are pursuing?
So actually, 70% is the early phase. There are several variations among different types of cancers. For example, the Hodgkin lymphoma I showed almost 90% respond. So depending on the type of cancer, the response rate variable, quite variable. And also 70% was the studies carried out for the very terminal stage of patient. Now it's getting better, but still certainly not 100%. Maybe currently 50% to 70% effective by combination of CTLA-4 and PD-1. But still, even though 30–40% non-responder. So why and how we can make it 90–80% is a big challenge in the cancer community at this stage. And I don't have any clear direction. If I have done already.
Yeah, so if Dr. Honjo or his team has a direction, maybe his team will follow up on the research. Okay, now we can open the floor to everyone in this room to ask questions to Dr. Honjo about his research, about cancer treatment, about the immunotherapy at large, and about doing research as a scientist in life science. I believe in this room we have a lot of people who are from the same field. If you have questions, you can raise your hand and I will see you. And if you raise your hand, I will point at you and you can ask your questions. And next to your seat, each of your seats, there is a microphone. Do you see your microphone next to your seat? Okay, you can use the microphone. If you didn't see the microphone, our staff will run toward you and give you the microphone, okay? Anybody with questions? Okay, this lady first.
Yes. May I ask one question is about your slide? Because there's a company, some company is research about the vaccination, about antigen. So as you said, so many years there's no succeed. May we know why?
Okay, the question is one type of cancer immunotherapy, they identify the tumor-specific antigen and use this as a vaccination tool to boost the immune response. So they actually identified many different types of cancer-specific antigens. But all the clinical trial didn't show any effectiveness. The reason, what I think, I had a big fight with this guy who are pushing this cancer vaccination therapy. So my argument is the cancer patient have already big, tumors and lots of antigen released in the body. And if you give additional antigen from the outside, it won't give additional stimulation. Already, you should have enough antigen in the body. Once you have tumors, big tumor. And that's my understanding. So the point is not the stimulation phase, but the release, the break. The immune system is overwhelmed by big tumor, and they got a very negative stimulation. This is the one type of regulation. When you give too much antigen to the body, the immune system become kind of tolerant, become silenced. And this is the state of the cancer-bearing the patient immune status. That's why I think it's ineffective.
Okay, good. Any questions? The lady next.
Thank you for your answer. I have a little bit follow up because you are talking about that if we want to the immune response to kind of the fight for the cancer, that there is the initial phase and the effector phase. And I wonder if you use the antibody to kind of inhibit the PD-1 and that the T cell can kill the cancer cell. That means the T cells still need to recognize the cancer cells. So you have any idea that is that possible that cancer cell kind of hide themselves so the T cell cannot recognize the cancer cells? Are there any possible mechanisms?
So basically, the immune cell can recognize any antigen which are different from our own body. So most of the tumors express non-self type modified antigen. So they are recognized. But the recognition itself doesn't mean the attacking against the tumor. You need several steps. One of the steps is the releasing of the break. that's why the key point is the break suppression. That is actually what we see. Okay, so theory comes later. It actually works by blocking the break. So, but what I mentioned about the why we cannot cure everybody, but still 30% or 40% remaining, we have many unknown factors. Immune response is very complicated. We can explain what we know, but there are many others which we don't know.
Thank you for your answer. Actually, I have another question because I actually is the virologist, so I study virus. And so I look at it that you found a PD-1, and in 2003 you kind of have a study about PD-1, the relationship between PD-1 and virus infection. So can you talk about at that time why you choose the virus and then go directly to the cancer study, or you still doing some virus research?
So we published a paper, I believe, 2003. So we used adenovirus as a model system. We labeled adenovirus with not luciferase, but some enzyme, and we give the adenovirus to the PD-1 deficient animal and wild type, and there was a very clear difference of the clearance of virus. PD-1 deficient animal cleared by week, or adeno gone. But so clearly, immune system accelerated, and they attacked the virus very efficiently. And the reason why we pursued tumor instead of the infectious diseases is because it's more important for the medical reason. But in the patent, we describe the infectious disease as well, so it can be used.
Another question over there, lady over there in white.
Hi, thank you for your great presentation. I think 30% or 40% response rate is good enough compared to other drugs. And I have a question. You mentioned that 30% of patients do have response, right? And I would like to know, any patient's immune system has become too active to control? Any patient who has response?
Yes, actually that is the side effect by hyperimmune response, and some patients develop the fibrosis in lung. This is very dangerous cases, and they observed several cases during clinical trial, and you have to stop. But unfortunately, few cases, patient died. So that's why I always stress, especially the cancer specialists are not the expert of the immune diseases. So you need the collaboration of the specialists. So this type of the treatment should not be carried out in a small hospital. You need many specialists, including immunologists as well, and then have to be followed very carefully.
Good. Okay, please.
thank you, Dr. Honjo, for a speech. I'm Olivia Chiu from National Chinchu University, and I'm majoring in law. So I will, I will ask a kind of different question.
Yes. Okay, this is the not my specialty, but certainly patent has two aspects. One, the patent protect the scientists or inventors and encourage their right. For example, my patent, so the patent I applied should have been done through university. But at that time, university has no power. Therefore, I asked the company. So all this product is the efforts by the scientists in university. So the university should get fruit from the industry. And that is very important because nowadays, I don't know in Taiwan, but in Japan, government has a huge deficit and the money to the university is going down and down. Therefore, scientific activity fortunately hit the right target and make us some money. It should be put back to the academia, and the academia should use this money to stimulate young generation to support their life and research. And this positive cycle is very important. So therefore, that is, I'm supporting the patent system. But on the other hand, the patent protected new medicine costs a lot. And I heard this PD-1 treatment costs the 10 million yen per year in Japan. So it's an enormous amount of money. But fortunately, it's covered by health insurance. So the patient don't have to pay. It's only 1/10 or so. So in Japan, it's okay. But still, for the rest of the undeveloped country, it's an enormous burden. So this solution is very difficult. Some countries like India don't want to accept the patent for the life-saving medicine, like HIV drug or those. Yeah, so WHO, for my friend, Professor Mitsuya, who developed the medicine for HIV, I think he donated the patent through NIH to WHO to provide the medicine relatively cheaply to the developing countries. So there are many ways, different aspects, and I don't have the answer to every problem.
Okay, sorry.
Hello. Thanks, Dr. Honjo's speech. I wanted to know, as your speech said, maybe you will combine your research and the irradiation or chemotherapy in the future. I wanted to know, have you already tried this combination in your research?
So straight answer is no, because I'm not working in the clinic. Okay, I'm just treating only mice, not the human. But I understand there are many that type of studies being carried out in many clinical laboratories all over the world. So
things are happening. We can get some coverage about the research thing like that. Okay.
Thanks, Dr. Honjo. I have a question. As a medical researchers, we have sometimes we have to face that our research fields is not that practical in medical practice, in some ways. So how do you say something to those students? Their research field is not that popular in the medical field. Because at first we don't know the research is useful or not. So how maybe some post for them. Okay, thank you.
So if I understand correctly, some area of medical research you cannot see immediate application, and in that case, how you keep your motivation? That's the question you want. So that's a point I want to raise. So when I started the study on PD-1, I never expect this leads to me cancer immunotherapy. So you never know. So these days, I think this is kind of the very infectious diseases of the politicians. Everywhere in the world, politicians ask the translational research. And many funding shift toward the immediate application translational research, and that is very bad, especially for the life science. So the life science is, as I said, very complex combination of many factors, and you never know what will lead you to the application. So understanding basic mechanism is always very important. But the reason why I try to use PD-1 to cancer is because I have medical background. I originally studied as a medical school and always intended to use my research for human benefit, welfare. So I always thought if my research develop into the even a slight possibility, I should try. So that's, I think, is important. And you always discuss with the clinicians and others and ask their opinion. But probably they may not agree, but you always have to keep in mind, once you have a chance, you can try. But it's not that, immediate. That's all I can say.
Yes, because Dr. Honjo, similar things happen in Taiwan. How politicians are shifting the budget to more applied science and technology. And I think this is something that our science community need to do something. Yes. Okay, any other questions?
Dr. Honjo, do you have any updates on ovarian cancer that have been treated with anti-PD-1?
So the clinical study we showed is a very phase 2 trial, and we are now designing a phase 3 ovarian cancer clinical trial starting very soon, and this will be international phase 3 trial.
One last question, if there is any question. Okay.
Yes, I have two short questions. Thank you for Dr. Honjo give us such a fantastic speech this afternoon. Actually, I'm from the biopharmaceutical national program. I work for the government. And I would say Taiwan government put a lot of effort to push the academia research and go into the clinical or pharmaceutical industry. And we did a lot of work to protect intellectual property, for example, like you say, for the patent. And I was wondering, because I would say the university, especially for the academic research, is the cradle of the innovation. And how do, according your opinion and your expertise, and how do you tell us, especially for the young scientists, to do the innovation, but not the quick and very fast applied science? That's my first question. And the second part is for the PD-1 story. We know a lot of the patients, they belong to a non-responder. So would you see a lot of patients from the non-responder, are they almost the immunocompromised, or they have something happen for their immune system? So that's why your antibody cannot work very well. Thank you.
It's not a short question. The first question, this is, I think that's a very difficult question. So, not only Taiwan, but also in Japan, now the very strong pressure to link academia to industry and facilitate so-called medical innovation. So, it's, I think, a trend. But it's not that simple. So first, as I said, biology or medical science needs lots of failure. The chance to succeed is 1 out of 100 or even less. So you need lots of gamble. And so medical innovation is kind of a simplistic picture. Okay? You have to accept lots of failure, and that is not the fault of scientists. That's the nature of science, especially biological science. That has to be accepted by politicians and the bureaucrats, and they don't accept. This is a problem. Okay? And academia, I think, has to be more supported long-term and in a diverse way. It's unlike making a supercomputer or sending a rocket to the moon. It's very difficult to predict what's the problem. So therefore, we need many gamble. The best way to win the horse race is to buy all tickets. Then you can get something. So the second aspect, often government says transfer the knowledge of academia to the industry, but then what? Academia gets anything? They don't spell out. That's what I mentioned. So transfer the knowledge to academia to industry, and industry gets money, and money goes to where? They stay in the industry. They should return to the academia. This part is missing in so-called medical innovation proposed the Japanese government. I don't know the Taiwan government. So that's why I'm always complaining about the Japanese government.
Okay, thank you for your wonderful questions, and thank our two young scientists and Dr. Honjo for this wonderful afternoon. I believe we all have very fruitful result and understanding of the PD-1 story. And it's an honor, again, for Pensai and Commonwealth Magazine Publishing and Tang Prize to have Dr. Honjo as our speaker and to talk about so many things in this afternoon. And let's give a very round of applause to Dr. Honjo, please.